Welcome to sunny Minnesota. Today we're going to talk about the heat transfer equation and how it relates to patient warming. The goal of patient warming is to drive safe and effective watts, which is represented by Q, into the patient. By carefully optimizing these three variables right here, we can get Q to be maximized but also safe. And we'll explain each of these in a way that'll make sense shortly. Let's start with delta T. Delta T represents the difference in temperature between the two objects that you're trying to generate heat flow. You can imagine that if two objects were extremely different in temperature, let's say that you had a patient who was 36 degrees centigrade and you had an object that was 1,000 degrees, you could imagine that would not be very safe. And in fact, the safe threshold is well understood in the literature. It's represented by the Stoll-Henriques model, where patients can handle 43 centigrade, and they can handle that indefinitely without any kind of thermal injury. So delta T, in a sense, is bounded, where you have one object, the patient warming system, maximized at 43 C, and you've got the patient's temperature. Now, interestingly, delta T actually decreases as you rewarm the patient, and therefore its effect on heat flow is actually lessened with effective patient warming, but that's sort of a bit of nuance. Next, let's talk about H. H is the heat transfer coefficient. So you can conceptualize the heat transfer coefficient as, let's say that you had a metal plate touching a metal plate. They would transfer heat very, very effectively. However, let's say that you had a metal plate touching an oven mitt, and those objects wouldn't transfer heat very effectively, and that's why you would wear an oven mitt when you're taking a skillet out of an oven. So with safe and effective patient warming, you want your heat transfer coefficient not to be too high. And that's, again, when you think about that skillet in the oven theory. A metal plate would transfer heat so effectively that it could overwhelm the body's ability to safely remove that heat and potentially injure the patient. However, if you take the other extreme, if you had a heat transfer coefficient that was incredibly low, you wouldn't accomplish any meaningful patient warming. So with both forced air systems that use blowing hot air and the conductive fabric system called hot dog patient warming, they have relatively low heat transfer coefficients. However, air is actually particularly poor at transferring heat, and therefore air systems have to pump some 1,000 watts of heat into the room in order to only have 50 of those watts actually get into the patient. But we'll talk about the waste heat problem in another video. So if the heat transfer coefficient is bounded in terms of safety, and the delta T is bounded in terms of safety, there's really only one variable left that can meaningfully impact patient outcomes, and that is area, the square area in contact between the two objects, in this case, the patient and the patient warming system. So when a patient is in surgery, they're under drapes, but they might be exposed where the surgery is actually taking place. Then they're laying on a pad. Now, in that case, you might have very limited surface area above the patient in order to warm them. Forced air systems are limited only to warming above the patient based on the fact that you can't really blow air under someone without elevating them or something. So, and important to note that forced air systems have a so-called underbody warmer. That's just marketing spin. It's not actually warming underneath the patient. The only way to truly increase surface area for the patient in a safe and effective way. And that's the way that hot dog does it, is to warm both above and below the patient. And that is exactly how hot dog works. And that presents a competitive advantage that allows the Q to be maximized in a safe and effective way, and leaves your patients normothermic in a way that cannot be achieved at least 50% of the time in 2 hours, according to studies with forced air. Thanks for watching. Make sure to like and subscribe if you're into this sort of thing. And we look forward to sharing more of the science related to patient warming with you in future videos.